Today, we are going to talk about cyclic code syndrome calculation. Earlier, we have discussed how to generate cyclic code using systematic code and cyclic encoder. Through encoder and with polynomial division with the generator polynomial, we have generated cyclic code. Now here, the cyclic code syndrome calculation. So this syndrome is useful for the detection of the code vector. So whenever the code is transmitted at the receiver, which is received, whether it is equivalent to code vector or not. If the received code word is not same as the transmitted cyclic code word, then there is an error. That error indicates the syndrome. So we need to find out that error and we'll add that error to the received code word. We'll get back the original code word. So this is where the cyclic code syndrome calculation. So here the received code word is taken as R0, R1, R2, Rn minus 1. Okay. So n bit code word is received. So this n comma k cyclic code word is generated, a k bit message word and n minus k parity bits, and finally n bit code word is generated in the cyclic code. Okay, that is being transmitted and received as R. So if syndrome is 0, then that in the transmission we don't find any error. So then that would be R equal to a transmitted code word. If syndrome is non-zero, then there is an error. So there is an error. So received code word is not as same as code word. So in this received word, the polynomial we represent in the polynomial, the nth order polynomial R0 plus R1 plus R1x plus R. So this R2x square plus Rn minus 1 x power n minus 1. Okay. So this is the received word, code word represented in polynomial R of x. The quotient syndrome S of x is getting if you divide R of x with the generator polynomial. So receiver polynomial, receiver code word polynomial divided with a generator polynomial, we get the quotient as well as S of x is the remainder, S of x by G of x. This is the remainder. Okay, this is the remainder. So we need to find out that remainder. So the encoder for the syndrome calculation, this is what syndrome calculator we call, as similar to the generator polynomial we represented syndrome cyclic code encoder with the generator polynomial. The n minus kth order block that shift register, and here the received word is given at the input of the modulo addition, modulo adder. This is the adder. So earlier generator polynomial message bits are given at this modulo addition, and now the received bits are received code word is receiving, and it is given input at the input of this flip flop. So this is what the shift register having n minus kth order. So these are the coefficients G1, G2, G3, Gn minus k minus 1 as in the generator polynomial. G of x is we know n minus kth order. Okay, G1 sigma G I of x power I plus x power n minus k I equal to 1 to n minus k minus 1 like. So similar to this polynomial, we draw the coefficients J1, G2, Gn minus k minus 1. These are the flip-flops of n minus k. Rth order. So in nth order polynomial, x7, 4 code word, for example, we have taken generator polynomial as 1 plus x cube as before. The nth order polynomial is g of x as h of x, the product of the two polynomials. So the factors of the x power 7 plus 1 can be taken 1 plus x into 1 plus x cube, okay, 1 plus x square plus x cube. These are the factors with the modular additions, if it is satisfies, and g of x either n minus k third order, either this polynomial or this polynomial, you choose. I have chosen 1 plus x cube. So in that, this is 1 and this is g1 of x, and this is g2, this is 0. So g1 of x is g1 is 1, g2 is 0. This is n minus, this is n minus k flip flop. So this 1 plus x cube. So 1 plus x square, and this is x cube. So the received bits are given here. So this is the encoder. For every shift S0, S1, S2 bits are generated. These are the syndrome bits. So in this calculation, we have taken 1011 as a message bit, okay, and we generated the code word already earlier in the previous example, as g of x has taken 1 plus x cube, we generated parity bit. Parity bit is 100. So this is what parity bit B and M, okay, the polynomial. So this is the parity bits. So 100, 1011. This is what code word. We assume the received word is 1000011. We don't know this received word, either it is code word or other word, which is not a code word. So either R equal to C or R not equal to C, we don't know. So this is the error we need to find out. Where is the error and what is the error pattern? So in this syndrome calculation, so this is the encoder we have taken. This is the S0, S1, S2 as per the G of X. 1 and G1 and G2 is 0 here. So S0, S1, S2, the received code word is taken from LSB. This is LSB. So 11000001. So this is what from left or right side to left side, 11000001. So we are giving these bits, received bits, systematically in the sequentially into this encoder. Initially, the reset values S0, S1, S2 taken as 000. Now, what is S0? S0. The received word R is given here, and this addition, modular addition, come over from S2 while closing this gate S2. So this S2, previous state of the S2 is added to the incoming R received word, okay, received bit. So that is why R plus S2 dash is the present state of S0. So this one. Similarly, S1, previous state of S0, and this S2 dash, that is the previous state of S2, is added here. That becomes S1. So S0 dash, S2 dash is the previous state added to become S1. And S2 just by shifting S1 to S2. So the previous state of S1 is shifted to S2. So this S1 dash, okay, that is that S1, S2, S0 dash are represented previous states. Now the input R is given here. This is the R. So one is given. What happens? S0 R plus S2 dash. R plus S2 dash is 1 and 0 is 1. Okay. And S1, S dash, S0 dash, S2 dash added. S0, S2 dash. 0 plus 0, 0. S2 is S1 dash shifted. This one shifted here. Now 1 plus S2 dash. This is S2 dash. This 1 plus 0, 1. S0 dash, S2 dash. 1 plus 0, 1. Okay, this 0 is shifted here. Okay, next 0. Next 0. So this one 0 plus 0, 1. Okay, 0 plus 0 is 0. 1 plus 0 is 1. This is 1 is shifted here. Next 0 plus 1, 1. 0 plus 1, 1. This 1 is shifted here. So this 0 plus 1, 1. This 1 plus 1, 0. This 1 is shifted here. This 0 plus 1, 1. 1 plus 1, 0. This 0 is shifted here. Okay, last bit 1, 1 plus 0, 1, 1 plus 0, 1. This 0 is shifted here. So this is the syndrome S. S is 1, 1, 0. 1, 1, 0. So it is a not null. It is not null. Whenever syndrome is null, then R equal to C. When syndrome is not null, okay, then R not equal to C. We need to find out the error pattern for that particular syndrome. For finding error pattern, we required syndrome calculation for the estimation of the error pattern, we required parity check polynomial. As we know that nth order polynomial is the product of g, h and h of x. So we have chosen g of x is this, then this product is h of x. Okay. We can take h of x from this polynomial, the product as h of x. We can estimate the syndrome. From further generator polynomial, we can also take the generator matrix here, g of x. From there, we can also find out the h of x. Okay. Then see here, g of x is the one plus x cube, the first row in the generator polynomial. This is the parity coefficients and this is the unit matrix as we mentioned. Okay. So this 1 plus x cube, 1 plus x cube, 1 plus 1 x square, 0 x cube 1. So 1 plus 1 1 0 1. This is where 1 1 0 1. Okay. Next x power 4, x power 5, x power 6, 0 0 0. So this is where g of x. Now multiply with x, g of x, that is shifted version. This is shifted, one shift, one shifted once. Okay, shifted once. This row is shifted once, right side, and x square, one more shift, x square gx. This row is shifted once again. Okay, x cube g of x. This row is again shifted. You got this. So here you see this in generator matrix, as we get the parity coefficient of the unit matrix. So this is not unit matrix. So that is why this generator polynomial is not a systematic. we need to make this generator matrix as systematic. From this, G dash is taken. We need to generate a generator matrix as a systematic P and I. So this is what unit matrix. This is the parity coefficient matrix. R1 plus R3. R1 plus R3. 1, 1, 0 plus 1, 1, 1 plus 1, 0, 0 plus 0, 0, 0 plus 1, 1, 0 plus 0, 0. So this is what we got. Similarly, in the last row, these two ones must be 0. Then you can add R1 plus R2. R1, yeah, this one is added, this one added, and this one added, and this one added. This one is also added. Okay. Oh, so 1 0, 1 0 1 0 0 1. So this one, you add this and you add this, you add this R1 plus R2 plus R4, R1 plus R2 plus R1 plus R2 plus R4. Yes. 1 0 0 0 1 1 1 0 0 0 1 0 1 1 0 1 0. Okay, 0 1 1 0 and 0 0 0 0 0 0 1 1. So this is what we got. So this is converted as systematic. This is systematic generator generator matrix. This is now in parity coefficient and unit matrix. So as per satisfaction, the verification of GH transpose must be null with the relation of generator matrix and the parity check matrix. So then H can be chosen where G equal to P and I. This becomes I and P transpose. Then it will be satisfied. So then I is the unit matrix. Okay, this P is the transpose of this P. So this is the transpose of the P. You transpose this 1 0 1 1 1 0 1 1 like this. You transpose 1 1 1 0 1 1 1 0 0 1 1 1 0 1 1 1. So this is unit matrix 3 by 3. Okay, n minus kth order. So this is the parity check matrix. We need to find out the syndrome. Okay, from this MGH transpose, CH transpose equal to MGH transpose, that is null. Syndrome calculation is RH transpose is the syndrome. We know the parity check matrix, H transpose you take RH transpose. R is having some error, code vector plus error pattern. So C plus C and H transpose. This becomes CH transpose plus CH transpose. This is 0 as CH transpose 0. The syndrome is EH transpose. Completely depends on error pattern. Okay. Now, in the previous case of the received code word, when we got an error here from this is code word, we have taken some error here, some ith bit. Okay. Find out RH transpose syndrome calculation. Syndrome calculation, find this is H, find out H transpose, and then this RH transpose becomes find this R multiplied with H transpose like this. So this is what RH transpose. Okay. So 1 0 0 0 0 1 1. Multiply RH transpose. This is H transpose. Okay. And now this first row and the last two rows add 1 plus 1 plus 1 1. So that is 1. 0 plus 1 plus 0 1. This is 1. 0 plus 1 plus 1 0. This is 0. By multiplying, you will get this is the syndrome 1 1 0, not null. There is an error. What is the error pattern here from the syndrome 110, which is the row of that 110 in the H transpose matrix, because EH transpose is also syndrome equal to 110. So if you multiply the error pattern of this fourth bit, that becomes E multiplied. This is E. Okay, this is E pattern. Multiply with EH transpose. This you will get the 110. So that is how the error pattern of like this. Add 0 0 0 1 0 0. So add this received word and the error pattern R plus C, R plus E becomes C. This is the code word. We retrieve the original code word. So this is what in the cyclic code, the code word is transmitted. Whatever the received word, having the syndrome or not, we have to check the syndrome. If the syndrome is calculated, if it is a syndrome not null, so there is an error. We need to find out the error pattern corresponding to that syndrome, EH transpose. Then add that error pattern to the received word. We'll get the code word. Thank you.